Look at these two charges, one positive, one negative, bound together in empty space. They exist in a state of permanent tension, creating a specific distortion in the electric field around them. This graph shows the behavior of a single, isolated point charge. Its electric field strength decays at a rate of 1 over r squared. If you double your distance from the charge, the field strength drops to 1/4 of its original value. Our two tethered charges form an electric dipole. It consists of two equal and opposite charges, separated by a fixed distance denoted as 2a. When you measure the electric field of this dipole from a distance, the field strength doesn't follow the standard inverse square law. It decays significantly faster, at a rate of 1 over r cubed. This steeper drop-off is the mechanism that governs how molecules detect and interact with one another across microscopic gaps. We have two individual charges, both radiating fields that reach out infinitely. This raises a paradox. How do two infinite forces combine to create a strictly localized, rapidly fading field? The answer lies in destructive interference. At any given point in space, the positive charge pushes out, while the negative charge counters it with an inward pull. This cancellation is never absolute. Because the two charges are separated by a distance of 2a, they cannot occupy the same coordinate. Their fields are slightly offset, meaning they never perfectly cancel each other out in every direction. This interference only becomes the dominant factor when the observation distance, r, is vastly greater than the internal separation of the charges, a. To understand a dipole's behavior, we have to treat the pair as a rigid geometric unit observed from a significant distance. We begin measuring the net electric field at a point P on the axis connecting the two charges, distance r from the center. Here, the outward push from the closer positive charge is stronger than the inward pull from the distant negative charge. Applying the principle of superposition to combine the individual field equations introduces the terms r minus a squared and r plus a squared into the denominators. As observation distance r becomes vastly larger than separation a, the a terms become negligible. Simplifying the algebra, the remaining terms multiply out, leaving a final denominator of r cubed. Along this axis, the two fields are in direct competition. The closer charge always wins, but its margin of victory shrinks cubically as you move further away. Now we move point P to the equatorial plane, perfectly bisecting the dipole. This creates two diagonal field vectors, one pushing away from the positive charge, one pulling toward the negative. Being equidistant from both charges, their magnitudes are identical. Resolving these diagonal vectors into vertical and horizontal components, the opposing vertical components cancel each other out. This leaves the horizontal components to combine, forming a single net field pointing parallel to the dipole axis, but opposite in direction. When we apply the same r is vastly greater than a limit to this geometry, the result is the same. The field strength falls off at 1 over r cubed. On the equatorial plane, geometric symmetry forces the field to act purely in opposition to the dipole's internal orientation. To see if this mathematical approximation holds up in the real world, we need to test it against exact calculations. We'll use two 10 microcoulomb charges placed 5 millimeters apart and observe the field from a distance of 15 centimeters. In this scenario, the ratio of our observation distance to the size of the dipole is 60:1. Calculating the exact vector fractions for the axial field yields roughly 2.6 times 10 to the 5th newtons per coulomb. If we use our simplified 1 over r cubed formula instead, we get a nearly identical result. Therefore, at distance ratios as small as 60:1, this cubic approximation is physically and practically exact. In both the axial and equatorial equations, the charge magnitude, q, and the separation distance, a, always appear together. At large distances, the field only depends on the product of these two values. We use the bold vector p as a shorthand for this product. This is the dipole moment. By convention, this vector always points from the negative charge to the positive charge. This single vector p defines the dipole's entire external identity, making the specific internal arrangement of the charges irrelevant to an outside observer. We can push this logic to a mathematical extreme. What happens if we shrink the dipole until it occupies almost no space at all? This is the point dipole limit. It describes a theoretical state where the separation distance approaches zero, while the charge magnitude increases toward infinity. Throughout this process, the overall dipole moment p remains constant and finite. For an ideal point dipole, our 1 over r cubed equations are no longer just approximations for far distances. They become exact for all distances. Physicists use this abstraction because it provides a precise mathematical lens for analyzing real, complex atomic structures. We can now apply this point dipole model to the actual physics of molecules. In many molecules, like carbon dioxide, the centers of positive and negative charge overlap perfectly. This symmetry results in a dipole moment of 0, leaving the molecule electrically neutral to its neighbors. However, in polar molecules, these charge centers are physically separated, creating a permanent electric dipole moment. Water is the classic polar molecule. Because its charges are offset, the molecule acts like a tiny compass needle. When an external electric field is applied, these asymmetrical molecules reorient to align with it. The dipole moment P acts as the lever. Because the charges are separated, the external field can pull one end while pushing the other, exerting the torque required to rotate the molecule. This 1/r³ decay rate defines the limited range of these interactions. It is the physical boundary that dictates how water molecules rotate to heat food in a microwave, and how engineers manipulate charge distributions to design new materials at the molecular scale.